I want to stop recording. Start recording here.
It's still
Okay.
computer labs, right, Kurt?
Yeah, that's probably.
Are
I'm sorry.
there
Yeah,
two computer labs?
yeah. So we could all come in at the same time during lab. I know, some of you may have to quickly make arrangements if you're coming in on your off day for lab, but it is our regular school time. I will have to. I can't promise anything though because actually I know on Thursday I think 8 o'clock, 9 o'clock the labs are occupied, but I'll double check with that and see what we could do. Heaven forbid we run into another student. Anyway, so I'll figure that out. We'll figure that out. Maybe we'll just skip it entirely, right? You guys wouldn't mind. Anyway, so the first thing I want to talk about, we have 3 modes: A mode, B mode, which kind of makes sense, and the last one, not actually C, we jump all the way to M. So those are the 3 modes we talk about in chapter 11. Now it's funny with A mode, I tell my students all the time, every semester, you guys, we have to learn about this, but you will never actually see or use A mode. And wouldn't you know, I have a student who just got a job recently with an ophthalmologist, and she is doing scans of eyeballs, among other vessels and such in the head. So interesting. She is scanning eyeballs. I didn't think I'd ever have a student graduate and do that. But A mode stands for amplitude, and it's, I mean, like I've never seen it in use. We'll have to. I told my former student that she can come in and do a demonstration or show some images of what she's done and talk about that. But A mode stands for amplitude. With this kind of imaging, we actually don't get an image. On page 160, the second image there, figure 11.3, it shows a ultrasound image, but that is actually a superimposed ultrasound, which, by the way, don't do this. Don't put the transducer to your eyeball. You could take your retina on and do some damage. But what they've done there is they've superimposed a regular picture, a regular ultrasound image, on top of an A mode, just so you could see what's happening. And I've done the same thing here. I've kind of created my little eyeball to show you. And now, if you guys have ever seen an oscilloscope works by, it's like a line is traced. Line's just always going across, and maybe it does this or something. But it's a continuous line, and when it gets to the end of the picture, it just starts over again. And then it does whatever tracing it does. And basically that's what you're getting here is an oscilloscope type image. So in other words, when I say an image, I just mean a peaks and valleys. Now this is not a waveform. What it's actually showing is actual physical things, physical echoes, but not in the way that we're accustomed to seeing them. So if I were to draw out in using this eyeball up here as a kind of a guide as to what we're seeing, let's say, let's just say, well, we kind of start over here, but I'll just go it kind of comes along at more or less nothing. And then it gets to the outer edge of the eyeball. It gets to right here on the eyeball, and suddenly there is a spike. That spike, all that's saying is that there are echoes coming from that depth. So its depth is here. So it is a depth finding machine, just like our transducers are. They're depth finders, really. And the amplitude is shown by the height of the spike. And so let's say the very first spike that this transducer sees is, well, actually your eyelid is closed when these are done, because the ultrasound goes straight through the eyelid without a problem. So let's say this is the eyelid, and then there's a little bit of a downward spike, and then right after the eyelid, of course, we hit the eyeball itself. And let's just say that produces maybe even a smaller spike, but then it hits the lens. So we got maybe with the hit the lens here, and the lens is going to create a larger spike. It creates a larger, and I'm not an ocular expert, so I'm not 100% sure what causes the stronger spike, the eyelid, the surface of the eyeball, or the lens, but I'm just kind of making that part up, because that's all that really matters, that we understand what's going on here. So in my world, in my made-up world, the lens has a higher, let's say we're going to call that lid, whoops, with a backwards B, at least I recognize it was backwards. That's the eyelid right there. And this is the lens of the eye there. And let's see, let's just say, well, after the lens, we go back down and we just start going all the way through this vitreous humor. Basically fluid, basically no echoes are being produced. So no echoes, no echoes, no echoes. Now this person has a detached retina. So once it reaches that level, it's going to have a little bloop. Now, if you're an ophthalmologist and you're reading this, you'll know that that doesn't belong there, because then we'll get to the back of the eye right about here, and you'll get the strong back of the eye, whatever is going on here as we go further into the optic nerve, and so on and so forth. So let's just add, so that guy there refers to that guy here. So that's the retina. And here's the back of the eye. What's that? The fovea, right? It's like the middle of the back of the eye, I think. Fove, and then optic nerve. So this is all you get from a truly A-mode only transducer and machine. This is the extent of your image, or your so-called image. You just get a bunch of peaks and valleys. The advantage of these is that they're very accurate on their depth. And they're able to make very precise measurements. Let's say, I don't know, let's say a normal measurement would be from the lens to the fovea. I think it's called a fovea. And that's whatever, it's 28 millimeters. I'm just making these numbers up, by the way. Let's say 28 millimeters, and then the doctor says, oh, well, your eye is too short, or it's actually, maybe it's too large. It's getting filled with too much vitreous humor and it's expanding, or however, whatever it is they do. I don't really know, but this is basically it. So it has very accurate depth. And then the amplitude, the strength of the amplitude is shown by the height of the peak. So it looks like the lens in my picture has the highest amplitude echo, and the fovea in my picture had the second highest amplitude echo. And that's pretty much it. So let's see. There are a couple. Oh no, that's next chapter. Amplitude mode. Strong echoes create tall spikes. Weak reflections create short. Yeah. So this would, the retina, just this flapping in the wind, would be relatively weak, and of course that is relatively strong. The x-axis, and remember this, guys, x and y, because one of these gets a little confusing. Let's go back to it. The x-axis is horizontal. Horizontal x-axis is giving us depth. And then we have the y-axis. That is the vertical, and that is giving us amplitude. And gosh, I don't really have much else to say. I hope this made sense, and I think in the book it actually gives a pretty good indicator of how these work as well. The big thing to know, the big things to know. All right, I want my real color. There we go. Once again, know your x-axis, your y-axis. Amplitude is on the y-axis. Depth is on the x-axis. It's very accurate with depth, and that's really why they use this. They want to make very, very precise measurements. That general ultrasound, we make pretty precise measurements, but this is even better. All right, there's not much else I could say. The next mode we have, guys, is called B mode, and this gets a little confusing. The reason it gets confusing is because some authors call B mode what we use on a daily basis, what you guys have been using, they call that B mode. B stands for brightness mode. And other authors like Edelman here says, well, B mode was the precursor to what we currently use. And so he says what we currently use is live, but it's still a B mode. So as you can guess, this is basically what we use. What he is kind of describing is the original B mode images were static. There was no live imaging. It's more like an ultrasound x-ray. You would just get a single picture. Yeah, you would get that picture. You'd actually go to film like x-rays used to. And then you would attain another picture. And there was no live action, as it were. One image at a time is the original ultrasounds, which, yeah, that would not have been very fun, honestly. So B mode, brightness. B mode appears as a line of dots varying brightness. B mode displays are created as follows. Okay, when he talks about an invisible dot, a sound pulse is emitted by a transducer. An invisible dot moves at constant speed across the screen's display. Let me just see, we used to have to learn how televisions worked a long time ago. And
tube and vacuums?
yeah, we used to have to learn like how that worked. Actually, I think there is, we slightly get into it. We don't get into as much as I had to when I took physics. So the old tube and vacuums, what they would do is that today's technology is amazing, but what I'm amazed is what they were able to do to create the original television screens. They actually created an electron beam, a beam of electrons, and it would come back from a little electron gun at the back of the TV, or oscilloscope or monitor, whatever you want to call it. They're all kind of the same. And so that electron gun would simply fire electrons. All right, big deal. Well, what there were ring magnets around that beam, and those magnets were very precisely manipulated through electronics, well, through vacuum tubes at the time. They were manipulated to steer that beam. And so that beam, what actually was happening is, let's see, I need a precise, no, I'll use that one. The beam was going across the screen like this. It would go across, cross, cross, cross. And as it went across, if there were, in the case of ultrasound, if there was no echo, and in fact, the image you have on page 161 is almost a negative because no echo actually produced a white dot. In other words, no dot, white. So on the original information, the original screen, if it were white, it was backwards. There'd be no echo. Today, in our machines, white or echogenic means a strong echo. But anyway, it'd be going along and it'd be coming along here, and then there'd be an echo decided by the computer to be exactly at this point. And so there'd be an echo, and then it would continue on. And as it came across again, there'd be an echo here, maybe an echo there, and then this line would continue on. And what would happen is, over dozens of lines, an image would start to form. And so I don't know what this image is going to be. I really didn't pre-plan this. You know, some kind of structure like that is formed out of this line that's simply going across, and it goes across regardless of whether or not there's any information. So it just goes. Here, it just. And then when it gets to the bottom, it goes back up to the beginning, and let's use a different color, and it just starts all over again, creating lines and creating specific points on that line if there is information that needs to be put down. In other words, if there is an echo from that location. So that's what they say. This invisible dot moves at a constant speed across the system's display. They're talking about old-fashioned television. Televisions don't really work like that anymore. Of course, we have everyone has flat screens now, and there's all sorts of different ways of creating a flat screen, but it doesn't involve an invisible dot just sweeping across. So when a reflection returns to the transducer, in other words, an echo returns to the transducer, is processed, and an invisible dot is turned on to create an actual dot. The brightness of the dot indicates the strength of the reflection. Okay, let me just take a quick look back here. On A mode, the height, I know this is getting really messy over here, but that is this height, or anywhere along that line, is echo strength, and that was in the Y axis. So very bright echo, it'd be high up on there. Very weak echo, it'd be low. we have to think of a new axis, an axis that actually would be a little harder to see. Because every time we look at a screen, it's two dimensions. We see an X and a Y axis. We don't really think of it that way, but we see X axis across the bottom, Y axis top to bottom. But we could imagine there's actually a third axis, an axis that comes straight out at you. So we have, in essence, our X.
Why are you going into trigonometry?
I know, and what this is the part that drives me crazy. I even have scribbles in my book that I can't erase because I went straight into my book. Yeah.
But we're reliant on that z-axis when we go into 3D mode, aren't we? Like if we're going to take images for the child in OB.
You're right in the sense on 3D is looking at three different axes, X, Y, and Z. But for the display itself, the Z-axis is almost an imaginary axis. Now, what I just had to quickly stop and look at, notice how in ultrasound, and this drives me insane, I don't know why they have to do this, but they've put X-axis on the up and down, whereas before it was Y-axis. But here's the thing, X-axis on both the A mode, which is on the horizontal, and on the B mode, which seems to be, from our picture, to be more on the up and down, on the vertical, they're both referring to depth. So that's the good thing, X-axis is depth. Y-axis actually does not exist, in the sense that when you create an individual line of information, there really is no left-right information. It's all X-axis, up, down. In other words, depth, 13 microseconds per centimeter. If you wait 26 microseconds and you hear an echo, it's going to say, there's something at 2 centimeters. The Y-axis for individual beams does not exist. It only exists in our world because we stack beam, 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 beam right next to each other. Then we create a Y-axis. But if you really get down to it, there is no Y. There's a Z-axis. Now that's imaginary because if this is our screen down here, X-axis is up and down. We'll put in fact, we'll put a little echo right here. Or at least a pixel, let's say a pixel. Because an echo is what we're receiving. A pixel is what the computer is putting on your screen. We have modern flat screens have millions of pixels, whereas older TVs had 1,000 pixels, or maybe a few thousand pixels. So our image quality has gone way up. But still, it really boils down to the smallest point is a pixel. So I just put a green pixel right there. The brightness describes the amplitude. So in a sense, let's say this particular pixel, or this particular echo which produced that pixel, was weak. So my X-axis is going to come out a little bit that way. Now you're like, wait a minute, what? All I'm saying is it's not very bright. The brightness is the x-axis. Oh, I like that. Brightness is, I'm sorry, and I said x-axis. I didn't mean that. Z-axis. The brightness is, so this is an imaginary arrow coming out. But let's say we have another echo further down, but it produced a much stronger echo. This whatever object in the body produced a much stronger echo. It's going to produce a stronger amplitude on our screen. In other words, on the z-axis, it's going to come farther out. But once again, that doesn't make any sense until we figure out that brightness is the z-axis. So in other words, this could be hypoechoic, whatever it is. And this one is hyperechoic. So the z-axis, I'm just going to go ahead and write it's imaginary. It's kind of an imaginary axis. But you know what, just keep in mind, imaginary, my terms, not Edelman's. So because I'll probably say something wrong by calling it imaginary, but it's in my brain, it's imaginary. So let's just read this. The x-axis of a B mode represents depth. Yep. So that's our screen. That is our depth, or at least distance from transducer, which is basically the depth, which is derived from the time of flight information, 13 microseconds per centimeter. When displayed on the oscilloscope, we don't use oscilloscopes anymore. The amplitude information of a B mode is routed into the z-axis. The imaginary z-axis is brightness. B mode was the first form of grayscale imaging. It is the basis for all other types of grayscale imaging. Note, some authors use the terms B mode or B scan to describe any form of grayscale imaging. And I would say most authors do that. So I had another picture up here I didn't even end up using. Let's just play with that a little bit. So I guess we'll just produce some echoes. This echo, this is whatever structure this is, this first structure is hypoechoic, produces a weak echo. The next one is a little bit stronger, so this will produce a little bit stronger echo. And the last one is the most bright, so that's going to produce the strongest echo. And arrow height indicates graphically the strength of the echoes. And so on our z-axis, let's just do this. I'll kind of create a the sideways. Actually worked so much better when I was, yeah, I can't draw it quickly, so I'm not going to draw it out at all, but in any case, stupid thing. This could be, that could be a weak echo, medium, strongest echo. And all of this is brightness. Strong echoes, more bright. Weak echoes, less bright. Does that make sense? Does this B mode and the Z axis make sense to you guys? I can't see you shaking your heads, so I'm gonna have to, someone's gonna have to speak
Nope.
up. No?
It's
Did I hear
like I don't know. It's like I get bits and pieces of it, but not all of it.
Okay.
That makes sense.
No, that's fine. What else can I say about this? Sound beam comes down, produces weak echo, medium, strong echo. Yeah. No. Okay. Well, let's draw these three. Here's our screen. Let's see, here's our first object. Here's our second object. I think I made that, fill that in brown there. And then our last object down here. Okay, so we actually see on our screen are three objects that were scanned with ultrasound. Echoes came back. The echoes were processed. They said this one took 13 microseconds. That's 1 centimeter deep. The first one, 26, 39 microseconds, whatever. And we've placed our echoes on the screen according to the time it took. Now, that's one aspect is time. The other aspect is how strong each echo was. And so the imaginary arrows that I was drawing before kind of came out like this. It's as if it's coming out directly. But this is a measure of brightness. So we'll call this weak, or let's call it weak. It's just easier to write than hypoechoic. This one comes out at you even farther because the echo was stronger. Since it was stronger, it produces a, we'll call this moderate, and weak. How about this? Let's say black on the screen or near black. Moderate would be some kind of gray. So not as dark as black, it's getting a little bit, that's a moderate echo. And then this last one was quite bright. And so there's like this imaginary, these are totally imaginary arrows. And this is, I know I'm spelling bright incorrectly. It's just the easier way of spelling it. Bright, in other words, white or echogenic on the screen. This is all Z-axis information. And we carry this other axis, which is X. And that is our depth. And this is our brightness, which is the same as saying echo strength. One takeaway is just to, over here, x-axis is imaged vertically. X-axis over here is imaged horizontally, but they're both depth. So x-axis is depth. I know it's confusing, and it's one of those things. I'm going to move along. If you guys continue to have problems with this, by all means, let me know.
So that was B mode, right?
Yeah, brightness mode. In fact, let's just write that down.
So the stronger the amplitude of the reflection, the brighter it'll be for us.
Yeah. Yeah. And that's why when you're scanning down and you see neck bones, those reflect a lot of sound, and so it's pretty bright on the screen. When you go through the blood itself, other than the noise we get on our screen, it should be pretty much black. It should be hypoechoic because there's very few echoes from the blood. So, all right. This guy we haven't really used yet. We played with it a little bit, but this is M mode. In other words, motion. So I've drawn up top, we kind of have a double screen. This is similar in how it's set up for like spectral, right? But this isn't spectral, this is not Doppler. In fact, this is acceptable to use for a fetal heart rate of a, let's say, a 6-week embryo. And the reason being is that you don't generally want to use Doppler, certainly not spectral Doppler. That's the worst Doppler to use on a 6-week embryo. People do it. You probably, if you're not sitting there for a long period of time, you're not actually going to hurt it, but maybe you will. And so you always want to be careful. You should never really use Doppler on a very early pregnancy unless absolutely necessary. And sometimes it is necessary. Doppler, we really haven't gotten into why, but Doppler does use a lot more energy. M mode doesn't. M mode is not Doppler. It is just simply grayscale. Now what we have is kind of interesting. You can steer your M mode. You can move your M mode from side to side. Let's just put this one right about there. So the entire line in M mode is your field of view. In other words, your field of view is a very narrow line. And so let me duplicate that line down here. Oops. So those two lines are equivalents. Now what we're going to do is we're going to draw this out over time. So here, and let's see, and depth is, let's just make sure that I get my X and Y correctly. X-axis is time, yeah. And y. So by the way, guys, it's just one of those things that he likes to quiz you guys on. What does x-axis tell us in M mode, in A mode, in, what is y-axis, what is z-axis? He does like those questions. Okay, let's come back to this. Actually, no, let's just use black. Okay, so, oh, by the way, and so what we're imaging here, if you haven't recognized it already, I've got, let's say, a 20-week old baby, and I decided to do an M mode on its heart. By the way, at 20 weeks, if you want to use spectral, you can let the mom hear the baby's heartbeat. Generally, you can. Maybe some doctors will be like, never use it unless you absolutely have to. But at 20 weeks, you're certainly less likely to cause any kind of damage. But at 6 weeks, we're talking about an embryo the size of a grain of rice. And so you got to be careful. So on this picture, though, we're going to draw this red line out over time. And let's just add a little bit of, let's just say there's just tissue up here, different types of tissue there and there. And as this is going across, first let's just do more or less that level. And so we're going to see this kind of drawn out over time and not much going on. Maybe there's a few levels of this. So what I just drew here corresponds to the picture. Let's do that again. Right about there. Not much going on. I could have drawn a little more motion in there because when the heart moves, everything around it moves, but I didn't draw much. Then we get to, let's be very specific here, then we get to the wall of the heart. And I'll draw this in green. And let's say the wall of the heart is going so what does that mean? That means if you're looking at the wall of the heart and the heart is beating, obviously the wall's moving back and forth. That's obvious. We all know that. What this is showing is back and forth and back and forth, drawn out over time. And let's do a purple. Let's show this part in the middle of the, let's see, left atrium. I assume it's the left atrium. It could be the right atrium. You never know how you're looking at the baby. Right, well, you know what? This is just fluid. This is just blood. How do I draw just blood in? Here, I need, well, that's going to be represented by pretty much nothing. There are no echoes coming back in the blood inside the atrium, so you really get nothing. But then we hit the second wall of the atrium. Let's use this color blue here. Then we get to that wall. Well, that wall is going to be moving back and forth, of course. So, and it's going to be moving at the same, let's see, but it's going to be opposite. All right, this baby's got a weird heartbeat. So the blues, I'm sorry I used purple up there for this one. Let's, okay. So now the colors are starting to match up. The green is the first wall that we run into. The black is fluid. It's just blood. We don't see anything. Then we see the what's really the wall, but the septum, the interatrial septum, that's moving back and forth. And then looks like, well, let's do another little. I'm going to fill this one in a little bit more because that's bigger. And then we have that little section right there of just fluid. So we'll kind of sneak this in there. That corresponds to right there. Let's do another color, red, work. Then we get to the valve itself. The cool thing about valves is they come in and out of the picture. Because as you're scanning down, you have to look at look at me here for a second. We're scanning down here, and here's a valve. Hopefully, it should be good. That valve is there, and as it opens, it's gone. There, gone, there, gone, there, gone, there, gone. And what you end up seeing is something like, whoop, whoop. When you see a discontinuity in M mode, that means it's in the beam, it's out of the beam. It's in the beam, it's out. I didn't really do this quite to scale because this entire box should correspond to this entire box, and I'm a little bit off scale here, but suffice it to say, we get another bigger black area of nothingness because there's no echo. And then we would, if I drew this correctly, we would run into the back wall, the ventricle wall, and then the then outside of the heart, and then continuing on. I actually have a video. Do I still have it? Oh, no, it's not that one. It's gotta be this guy. Please move this window away from share it. Well, no, don't tell me what to do. Okay, you should be able to see this. Yeah, well, I'm just going to go ahead and run this. It has Mindray. I actually used to own one of these machines. But let me just run this. And
okay, so our next topic is M mode, which is motion mode, and the exam type that we're using for here is OB second trimester scanning.
Okay.
So what we'll do is, along with your other modes and functions, you have M mode that's over on the far side of the keyboard. And when you hit that once, you get that green line. And what you want to do is line that up through your cardiac activity, hopefully at a time when the baby is not jumping all around.
Still, just a little bit.
Exactly.
Yep, still right now.
And now once you have lined it up through some of the chambers, now you can go ahead and press the M mode button again, and it'll start sampling through there. And as you get that,
nice.
You can go ahead and hit freeze.
okay, and oh boy, let's see if I can. Did not want that to happen. All right, well, I'm not sure where I know this is going to be very hard for me to see. You could look, there's barely a dot on the left side of the M mode. And you're just going to have to work with me here. As we're going through, this entire line from top to bottom is represented. Yike. Oh, God. Okay. This entire line is represented from top to bottom here. Let's go to the very, very top. All right, mom's skin. Assuming they didn't Nope, they didn't zoom up at all. Mom's skin is the very first line going across. It is perfectly still. Then this is a pretty skinny mom here. She's got a little hypoechoic layer of subcutaneous fat, and then another little
Under this
echogenic
setting, it's exam time.
another little echogenic layer right here. Let's see, what is that? A little bit of fascia, another hypoechoic layer, more of mom, and then this is all mom, 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 mom. Not much going on there. Then let's see if we get down to about, well, about here, actually, that actually is shown up here on the image. This is placenta for the most part, a little thin placenta, a little thin uterine wall. And then we're going to keep going down and down and down and down. And suddenly we're getting into, this is baby. And then once it gets a little hypoechoic here, that's actually the heart. The heart, as she's imaging it, is mostly fluid. We're not seeing a lot of walls. It's not the greatest location for a heart image, but this is fine. This is all heart from here to here, and then it keeps going on. Baby's chest wall, and then back into mom again. So baby looks like baby goes from about from here to here. The middle third of the M mode is all baby, and then the more hypoechoic section is heart. And we're not going over any valves, although this little dot just appears. And so there's something there that's only appearing at certain times, and then there's movement here. But each one of these movements is just simply drawn out over time. That's kind of cool. And by the way, people always ask, how do you measure the heart rate? Where do you put the calipers? It doesn't matter. If you're just doing a heart rate, we look for any repeating pattern, and you measure the time for that repeating pattern. It doesn't matter what part you're, as long as the baby and not mom, doesn't really matter where, as long as it's a repeating pattern. It looks like a heartbeat, it's a heartbeat. Okay, let's just play this.
Type with a curvilinear transducer, and you've selected your OB second, third trimester preset. You can hit the measure button, which is just on the top side of the trackball, and it'll automatically take you to fetal heart rate. That's a default measurement, so you don't have to do anything.
So if I'm in M mode and
Correct.
in OB, it will take
It'll know. It knows automatically that that's the one thing that you want to automatically do is fetal heart rate. So then you use the trackball and the set key to go ahead and select 2 full wave cycles. And it actually will tell you that up on the screen where you see your measurement. You're going to see that in the parentheses that it would like two full beats.
Okay.
Yep, correct. And that's something that we can change when the clinical application specialist comes out, and we can modify that.
Okay.
But 2 is the
Default.
the default and kind of the standard for clinical acceptance. And
Okay.
once you do it, you can lock that in, and you can save that, and now it's stored with the images.
Okay, great. And the same way to get out of this would be either to hit the M again or the B?
Correct. So if you hit the M again, you'll see that it takes you right back, and just like the B button kind of brings you back home. Yep, exactly.
So this is a good probably time to ask you about the zoom button, because we're looking at the heart, and a lot of times we would want to zoom. I don't think we've covered that yet.
Correct, yeah, and I think that there's a lot of applications in which you might use the zoom function. And so when you press the zoom button, go ahead, it'll give you a region of interest box, and this is where you can use the trackball and the set key to change the size of that box to cover the space that you want it to be in. You don't want it, if you're going to zoom, you're not going to want to have it be a super big zoom box, or else it won't do much for you. And once you hit that set button again like you did, it locks it in, now you can move it. And then when you press zoom now, it'll
Zoom
go ahead.
again.
Yes, it'll zoom in now on your region.
Okay.
And so that's a really great picture of a 4-chamber heart. And now if you do M mode again,
It would even enhance the M mode even more. And then M mode again.
you got it.
Okay, great.
And now you can see that's a marked difference.
Yeah,
So when you use the
right.
zoom, it really brought that up into full detail for the
Okay.
baby's heartbeat.
Okay, perfect.
Okay. Let's just get rid of that entirely. Okay. M mode, kind of making sense?
Yeah, after they zoomed in, it made a lot more sense. Like, oh, that's what we're trying to look at instead of just the prior one.
Yeah, and so M mode will look really different. Depends if your field of view, that line is on something that's moving a lot, it's going to be really obvious. And if it's on something that moves very little, then not so much. So the mechanical index for M mode is actually a little bit higher than just grayscale alone. And we really don't talk about mechanical index for a while, but I just want to mention this. So color Doppler on a 6-week, let me draw a little 6-week embryo. There it is. Color Doppler, don't do it. Mechanical index goes way up. We'll discuss why. Spectral. This is your entire, basically, that dotted line that I just drew, and that's your entire region of interest, and using a form of ultrasound that is much stronger. Definitely a bad thing. M mode is just grayscale. The mechanical index does go up a little bit because you grayscale the whole image, just like you're always doing, and then you grayscale right there. So then you do the whole image again, and then you hit this, and you do the whole image again, and you hit this. So basically the machine is alternating between taking the entire grayscale picture and then doing one pulse in that one little line. And then it takes the whole picture and pulse, the whole picture and pulse. And so it is kind of doubling up the amount of grayscale imaging on that one spot, but it's still grayscale. So the energy along that line does increase, but it's pretty negligible. But it does increase, in case there's ever a question on that. Wow, guys. Chapter 12, two-dimensional imaging. When we're talking about all of chapter 12, and so you know by now, Edelman wants us to learn certain things. You know, is it adjustable? What produces the wavelength? You know, those are certain things that he wants us to remember. It's kind of like a little bit of a teaching to the test, which is fine by me. On this chapter, shape and number of active elements in the transducer. So we're going to start talking about transducer design. We've talked about basic physical design, but we haven't spoken about all the different types of transducers, and there's a lot. Well, there's only several basic types, but there's a lot of variations on those. So the shape and the number of active elements. So for instance, this guy has one element. This guy down here has dozens, if not hundreds of elements. Automatic redirection of sound beams to create an image. What he's saying there is this a mechanical transducer, which this first picture is, or is it an array transducer, which the other picture is? Focusing. Some transducers do not, they have one fixed focus. Some have changing focus and changing numbers of focus. the shape of the image. So as you guys know by now, we have some images that are that shape. And we really haven't played with the other transducer too much, but we have other images that are semicircular at the top. Those are the two transducers we have. And consequences of a damaged or non-functional element. I don't know why he gets off on that. Mechanical transducer, first one. Mechanical transducer contains a single circular disc-shaped active element that is physically moved. This movement creates a scan plane. So we already spoke a little bit about a circular element, kind of like shaped like a coin. And, anyway, a single element and how a single element will actually produce a natural focus and all that. And there are single element non-mechanical transducers. They're basically like a little pencil transducer that you've probably seen in use. If you've ever, seen somebody get their pulse done sometimes, or their blood pressure. It's not always a stethoscope. We could actually do that with a single element transducer. But there's also a way, there's also a way of creating a more active picture. Most of those single element transducers that don't move or anything, they don't produce a picture. They're probably a continuous wave transducer. So no backing material on them. They just ring, 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 ring nonstop. And so they're used for vascular studies. But we can create a single element transducer that produces a picture. And it's done, well, mechanically. So a mechanical transducer, let's see. Oh, sorry, my screen's moving all over the place while I'm trying to write here. That says mechanical. You know what, I can't stand. Even I can't stand how sloppy that is. Oh, dang it. All right, good enough. Mechanical transducer, meaning the elements are moving. Usually they're spinning in a circle, one element. It produces a fan shape. So when we see this image on a screen, what we're going to see is, well, let's see. That's the shape we're going to see on our screen. Not a rectangle, not a bundt cake or slice of bundt cake. No, this is an actual pie shape. So they call it fan or sector shape. Swipe with the blade and pulses radiate out. Okay. So one of the things about this, and we'll find this with other transducers as well, is that, let's do every pulse is purple. The pulses all originate from the same spot. And each pulse goes down a different line called beam lines. And you could see there's a bit of an inherent problem in producing images like this. Now, sometimes these transducers are just awesome to use. They have a really small aperture, which means a small transducer, which means you can get it between ribs quite easily. They used to do mechanical transvaginal transducers, so you didn't have to have a really large transducer in order to do this. You have this pretty small transducer. But if you could see, there's a bit of a problem once you get into the far field. The depth, I'm sorry, the width in between lines gets wider and wider, whereas up here, this width is really not a big deal. There's probably enough overlap where there's really not even any loss of lateral information. But on this one, conceivably, you could have a small little object right here, and it's not seen, or it's a little, even if it is seen, it tends to be blurred out because the beam lines are spreading, and it degrades our lateral resolution. So that's a problem with these kinds. With greater depth, gaps of ever-increasing size exist between the scan lines. There are computer algorithms that kind of help with this, but still it is a problem. Beam steering. So we always have to talk about how the beam is steered, if it's steered at all. Two-dimensional image is built up by rotating the crystal with the motor. Sound beams are emitted as the crystal moves, hence the scan plane is created through mechanical steering. Now this is really amazing to me. That's not the right thing. Is how utterly fast everything has to happen for this to work out. Because, and I don't even know how the wires are attached to a transducer element that's spinning so quickly and spinning at all. So there must be so this is our element. And as you can see, that element is based on a wheel that is spinning at a high rate of speed. I don't know what the actual rate of speed is, but it can't be too unbelievably high, because what this has to do is produce a beam of sound. And before it goes too far, it has to record all the echoes coming back to it. So it's spinning fast, but the speed of sound is even faster. And so it does that, and then it does it again. Let's say this, we'll pretend this element is moved down a little bit more, and it shoots out another beam of sound, and then there's more echoes coming back, and so on and so forth. And eventually it produces our image. So this is called mechanical steering. We don't have in our lab any mechanically steered or mechanical transducers. I have used them in the kind of distant past, and I haven't had my hand on one in, well, certainly more than a decade. Focusing is fixed. And that could be internal or external. Just a quick reminder, let's see, an internal. So if I'm gonna I'll redraw this element here and bring that back up to here. And let's see. There's my element. It's not necessarily round on the back. I can make it look more square. But in any case, it has a concave surface. That concavity is going to force sound together, and it's gonna bring that focus up. So if you need to focus, if the natural focus isn't where you want it to be, you can bring it closer, but you can't can't make it farther. Can't do that. You'd have to change the entire design of the element itself to make it farther. But if you want to bring it up closer, you make it a little bit concave. That's internal focusing. And then, of course, there's external focusing, where you just have the transducer here. Oops. That's just filling in the transducer. And let's see, let's do a little acoustic lens, doing the same thing, bringing those sound beams a little closer together. That brings the focus to, let's say, here. Whereas if it were unfocused, let's just draw an unfocused transducer. Will still element will still have a focus, and let's just pretend it's down here. And so those beams, even though they come out straight, boy, they have a tendency to eventually find a focus and then spread out. So by the way, guys, I have a really awesome video for our, oh, that was something. On days, I don't know that I did this perfectly last week, but water under the bridge. On days where none of us are in lab, all of us have to do the asynchronous. So everyone does the asynchronous today. But I've got some cool videos that really shows focusing of the ultrasound beam. It's like single pulses of sound. They're really cool. Anyway. So let me just read through here, internal, external focusing. If you have a damaged crystal, what kind of picture do you get? Nothing, because there's only one crystal. If you only have one crystal and it's damaged, you get nothing, blank screen. So anytime it's you scared me. Yes,
Sorry.
sir.
Why is that? Because I'm having a difficult time understanding that aspect of if the crystal's broken, you don't get an image at all, because of having been in nuclear medicine. If the crystal there is damaged, if there's a crack in it, you end up getting two different images. So that it's throwing me off understanding how come you don't even receive an image with a damaged crystal on ultrasound.
Well, in this case, if your crystal is damaged, here's our little transducer crystal here, and I'll put a crack in it or something. I mean, I suppose it could be partially damaged, and then you got a bad picture, but generally here, in fact, instead of a crack, I'll put a single wire to it. A single wire going to that element, producing sound by hitting it with electric voltage, produces a sound. But if that one wire is damaged, then absolutely positively no image at all, because this is literally the only element producing an image. It's the only one. We have two transducers in our lab right now with one broken element, and it's hardly noticeable. But that's because there's hundreds of elements. On a single element, only that element is producing a sound, or yeah, that's the only one producing a sound. The only one listening to echoes. If it's broken, you're done. You're out of luck.
So is that so much more the wiring going to the crystal or the crystal itself?
Well, so yeah, I mean, if it's not the wiring and you crack the crystal, is there a chance that that something is still produced, yeah. But I think the damage is pretty significant when you crack one of these. At least in my experience, every time, like we don't really find partially working elements. They're either working or they're not. So
Here's a question. The crystal, is it acting as an amplifier for the sound waves? And by that, I mean, so like back in nuclear medicine, we have photomultipliers. So when it receives the light that's given off by gamma radiation, it takes it, multiplies it, and makes it bigger, it amplifies it so we can see it on the screen. Do the crystals here in the ultrasound transducers work similarly?
the crystal itself, no, but there are amplifiers. We really need amplifiers, and I'll tell you why. The beam goes out, let's say it goes out at 100 watts. And I'm just making up numbers again. It goes out at 100 watts. The echo that coming back will produce a, so the, here, I'm drawing it right here. Let's say, say going down is 100 watts. And then it produces echoes that come back, hit the crystal, and then the return electric voltage might be 0.0001 watts, or like in the milliwatts. So the difference between the strength going in, the strength coming back out is just really, it's huge. And with a wattage this small, if we didn't amplify it, literally by the time it went from the transducer to the machine, the computer, up to your screen, the information would be lost. It'd be lost inside of all the noise. And so there are amplifiers in there, but no photomultipliers though. So let's see. Mechanical, single, circular, disc-shaped, active element. It is mechanically steered. It is fixed focus, either by an internal or an external focus. You damage one crystal, you're done. And that's it. I think those are the major things to think about with that. And then we get into the fun stuff. Now we're going to be talking about arrays probably another couple of days, because these get pretty complicated, but I love talking about it. So hopefully we'll make it through. What am I doing? All right, I'm going to need whoops, no, I just need more. Okay. Oh, so exciting. Transducer arrays. So an array means many, or it's a number of elements working in concert, working together. What did I just do? So I'm just reading here, page 168, single element transducers. Mechanical probes are technically simple, have been replaced by more sophisticated designs. Generally, modern transducers called arrays contain multiple active elements. What you start with is a single slab of piezoelectric material or zinc, lead zirconate titanate. Yes. Cut into a collection of separate pieces called elements. Each active element is connected by a wire to its own electric circuitry in this ultrasound system Each element is acoustically isolated from its neighboring crystals. A channel is a combination of active element wire and system electronics. So each one of these is its own separate element, connected by its own wire, goes all the way back in. So each element, wire, and any dedicated electronics that go dedicated to that specific element is a channel. Well, let's just write wire here first. So element, wire, and we'll just say electronics. All of these together produce, that was a channel. I never know if I'm spelling channel or Chanel. It gets very confusing. All right. Let me get some of this, clean some of this up here. So one channel. Okay.
So is each one pretty much its own thing until they combine and become one whole picture?
Yes, each channel is individually controlled, and that's actually really important, that we have over control over each element separately, because what these engineers have done, and God bless these people, they're amazing. They time these elements with absolute precision. And in order to do that, each one has to have its own isolated, completely isolated from the others. And so various ways. Yeah, okay, we're going to talk about that. So I guess today we'll talk about, we'll only talk about the linear phased arrays today. Linear phased. Sometimes people just call them the phased or the phased array, and they just shorthand. But linear phased array, the footprint of the face of the transducer comes into contact with skin in small square, about 1 centimeter on each side. Linear phased array has no moving parts. The beam is steered and focused using an electronic technique called phasing. Let's just see. All right, so there's 100 to 300. So these tend to be small. They'll say, we'll just do a small. Small footprint. These are really good for getting in between ribs. So similar to the mechanical, that it has a smaller footprint. These elements are side by side, is rectangular and narrow. The width of each element is 1/4 to 1/2 of the sound's wavelength. So the width, 1/4 to 1/2 lambda. I bet you had to look that up though for the spelling of channel. So when we talk about the width.
Yes, I did.
The width of one element is here. So that's in this particular type, 1/4 to 1/2 of a wavelength. Now remember, that's not thickness. Thickness determines frequency. Thickness, width, yes. Here, let's get rid of some of those. So that's going to be in my way later on. All right. 1/4, 1/2 of the sound's wavelength. Image shape is once again very similar, and this gets me. This flat transducer, now granted, it's smaller in length than the transducers you guys are familiar with, but still, it's not that small. It still produces a fan shape. So it produces the same shape as the mechanical. I had to rack my brains on that one a little bit because obviously this isn't a point. It's not, you could see a pointy top maybe using a little mechanical transducer and saying, well, they all come from more or less the same spot. But this one is certainly not. It has a width. You would think the top of the screen would be flat. You would think maybe this, and this picture here, this would represent, the top of that picture there would represent the transducer face, but it doesn't. We actually have a pointy top on this, and I had to work this one out in my head. That was not easy. Two-dimensional imaging is built up with an electronic steering process called phasing. Sound beams are electronically transmitted. Whew, okay, now this is where things get, I think I do a little bit better on the whiteboard than I do here. I'm going to try it again anyway. You guys remember that, so each one of these is going to produce its own bubble of sound when stimulated. So on this one, we're going to stimulate all these at the same time. And then each one of those bubbles will expand out, and they'll continue to expand out. And you could see, this is what we talked about before with Huygens wavelets. You could see where you're getting all this constructive interference, generally in the middle, and out here you don't get constructive interference out here so much, and there actually is a little bit here and there. It's a problem, but for the most part, it's all in the middle there. And so we get this wavefront. And literally, these guys pretty much start to line up in such a way that was not very clean, but they line up in such a way that all the peaks and all the valleys are lining up perfectly to create this powerful beam in the middle, well, powerful beam. And on the outside, where these outside guys, these want to continue to move outward, but there's no constructive interference out here, so the beam outside of the sound outside of the beam is a lot weaker than the sound inside the beam. So that's basically how this sound is produced, right? Now that I've made a mess of things. So that was everything without phasing. Phasing just means time. There's changes in the time involved. So let's see, let's start. Whoops. Let's start by phasing every single one of these. So this is the first one to be stimulated. That's the second, third, fourth, fifth, sixth, 7, 8, 9, 10, 11, and 12. So 1 through 12, 1 being the first to be stimulated by electrons. Electrons are there. The second one, the electrons are a little bit behind. Third one, the electrons a little bit behind. Fourth, and so on and so forth. Until basically we've created an electron line that looks like that. This is the last electron up there. So there's a line of electrons, a line of voltages coming down these wires. It's just that number 1's winning and number 12's in last place. So let's see, number 12's in last place. Let's do number 1 is winning. I'm going to try to create one wave front, but let's see, number 1 was the first bubble. So you know, just think about this way: bubble, 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 right? That's how it grew over time. And then number 2 was just a little bit behind. So the bubble's going to be just a little bit smaller. Number 3 was a little bit smaller. Number 4 is a little bit smaller. Didn't give myself, I don't have the entire beam built yet, but that's okay. Can you guys see? There's my line of electrons coming down. This guy's winning. This guy's losing. This is the first element to fire off, which is why it has the largest sound bubble coming out of it. And let's see, I got 1, 2, 3, 4, 5. I only got up to 5, and looks like number 6 hasn't even turned on yet. But what we have here now is a wave front. Look at that. Look how, I'm actually kind of proud of that. My electron wavefront matches my sound wavefront. I've just created a beam of sound that is steered to, as far as where we're concerned, is steered to the right. If I, of course, had an electron wavefront that looked more like this, then the first sound beam over here would be all the way. You know what? It won't take too long. We'll just quickly, because it's worth taking our time on this. This is really important. So now we're going to look at the blue electron, or the blue voltage wavefront, and we'll make blue circles. 12 was the first one to be created, so it's a little farther out. 11, 10, 9, 8. Okay, once again. There's my wavefront. There's my electron wavefront. And now the beam is steered off in that direction. Oh man, I'm liking this. That actually worked. That's actually working out really well. So and this is all phasing is really timing. I'm believe the being focusing. So I'm sorry, I didn't read this prior. I'm pretty sure, and correct me if I'm wrong if you're reading through, the linear phase arrays, every time a beam is created, all the elements are used. I'm just not seeing that anywhere, so I'm a little afraid I'm saying that wrong, but oh, more about linear phase. All the active, yeah, so all of the elements are used every time. So every beam of sound is created by all the elements. That actually is the key to why it's a pointy top. Steering. You know what? Let's get to focusing first, though. So phasing is timing. Let's instead of oh no, I could leave those. Let's take this out. Okay, we're gonna set up some new timing protocols. So we're gonna have to ignore my 2 electron slopes. I don't want to erase them right now because I'm afraid that'll make more of a mess if I do. Let's instead of steering from right to left or left to right with our phased timing, we're going to steer from outside to outside at the same time. In other words, we're kind of going to double steer, which is really what we're doing. We're going to start here with 1 and 1 and 2 and 2 and 3, 3, 4, 4, 5, 5, 6, 6. So now, essentially, we're going to steer from both the left and the right at the same time, if that makes sense. So what's this going to look like? Well, this one, I need a new color up there. I'll just light blue, I guess. No, let's make it red. Let's see it. Okay, here, different size. Now my beam is going to be my electron phasing. This is the voltages coming through the wires is going to look a little more like this. If that makes any sense. This electron and this electron tie for a dead heat. They're first. These guys are second and third, fourth, fifth, and then the 2 middle ones are sixth. These guys, the number 6 ties for last. So that means, of course, our outside elements. Let's see if I could draw this. Make that a little bigger. Outside number 1. Outside number 1. Then we go to number, and so those were first. Then number 2 was a little bit later. It's not quite how it would be shaped. Let's just try that again. Nope, that's still too much. Oh, well, it's actually harder to do than one would think here, but I'm messing this up. All right, let's just draw. It's a little messy near the probe, and actually that is a problem. We can't scan very close to the probe because of that. Also because I drew it poorly. But here we have a wavefront that more or less is shaped like this. Ah, what does this look like? Look at this shape. Concave shape creates a focus by forcing kind of those outside, in this case it's a single element, so the outside of the beam is kind of forced towards the middle. That brings the focus up. Whereas a flat element doesn't, although there's, for some weird reason, just the way things interact, there's still a focus, but the focus is all the way down here, the natural focus. So electronically, we just achieved, oops, I got so close here. We just achieved the same thing. We've taken the focus. Now our sound wave is going this way, this way, this way, and you could see the focus is going to be right about there. So through phasing, we're able to steer right, left. We're able to focus by stimulating outside elements first, inside elements last. It gets really crazy without going into too much detail, but really, if you think about it, why can't we steer and focus at the same time? So in essence, you take this steered timing of voltages and just kind of lay it up on its side. I'm running out of colors here. I'm just going to use I have nothing left. Okay. Nothing left in my arsenal here, guys. We can focus it and steer it. So I'm just going to kind of put that curve here. That curve represents the timing of every element. So now this curve would produce a curved, ooh, okay, that's just getting ugly. Let's just say that we could both steer and focus at the same time. There's actually a lot of things that could be done even beyond steering and focusing. But all of that is done with precise timing of every element. Wow, I've pretty much covered, like 5 pages here. Oh, so I kind of covered, I did actually, I covered a lot of pages. And he takes a lot of time to talk about this because it is important. So page basically from 171 through 176. And then on page, oh my God, we're talking about multiple transmit foci as well. Let me first talk about, before we get into multiple focuses, let's talk about why this is pointy topped. Okay. Let me just draw a quick transducer face. There's my multiple element transducer. Those are all my elements. Why is it pointy topped? Why do we have a more or less shaped like that, like a party hat? Well, it's flat, so it's more like a piece of pizza. Pizza. On a
Would it be because of the way that the waves are sent out?
it is. It's the fact that we use every element every time. The two transducers that you guys are using in class do not use every element at every time. They use, it's all little groups of elements that we'll talk about next time. 1150, wow. Every element every time. And since it's every element every time, our sound beams are, what happens is that as we're holding the transducer down, it steers one way, then the other way, then the other. It steers the beam like so. And then a millisecond later, it's steering the beam like so. And then a millisecond later, like so. And a millisecond later, like so. Now, it still kind of creates, as far as I'm concerned, a bit of a flat top. But basically, as every one of those is created, basically I drawed it. You know, it was steering this way.
Are you from Arkansas?
Yes, I am. Oh, that was a horrible picture. Never mind that one. All right. It's really hard to picture. It's really hard to explain. You just have to memorize it. But it's the fact that every element every time is used. It always comes back to the same point. It always comes back to the face of the transducer. And it's the whole transducer. So it's kind of like a point source. I still don't really see why it comes up to a tiny little point. I would think, given the size of the transducer, it seems to me that it would still be a flat top image, but it's not. So it's not like that. It comes actually to a point. Those are linear phased arrays. So definitely go through those pages where it talks about steering. We'll end here. I don't need to go into focusing. We'll do that next time and continue on. Let's see. So what is next time? Tomorrow is, I can't think about how that works.
Tomorrow's vascular.
Oh, right. Duh. Yeah, vascular at 9:30. I forgot about that. 9:30. And then that's it. So, and there's no lab tomorrow, so no assignment tomorrow. We got assignment today. Everyone's got to do the assignment today, but nothing tomorrow. Wednesday, we'll continue with 12, and then we'll break and do some review for your test. Thursday, well, I'm still hoping to have a test. We might have everyone come in for lab. at the same time. And then, that'll be a double whammy. You take your test and you get credit for being there for labs. So that'll work out. And I don't know about Friday. That's thinking too far out ahead. Oh, and I suppose I don't need to be recording our plans.